So last time we talked about the formation of these enones, right? Another way that we could have called these are alpha beta unsaturated carbonyls or alpha beta unsaturated aldehydes or ketones or whatever you want to call it, right? So we have a generic structure of something like this, right? So you have R groups everywhere else, right? But so an enone, you got a double bond next door to a ketone. And so, well, again, we have to ask the question of, well, what difference does this make, or why do we want to do this, or why should we care, or any of these kind of questions along the way. So let's think here for just a second, or let's make an observation, right? If I take, let's say, this generic alpha beta unsaturated ketone, and I will put in some sodium ethoxide and sodium methoxide, right? If I do this, then, one thing that might happen is, we will do an addition, right? We will do an addition reaction, right? Where we just, whoop, right there, right? Now, of course, this is reversible, right? There's equilibriums to be established, all this kind of stuff, right? Honestly, this probably would, let's just say completely, right? Let's say it does that, right? So obviously this could be reversible, right? And we could, kick this back off and go back to where we started. But there was an observation made where if we have let's say we have this guy here, right? And if this was reacted with sodium methoxide, and we could put this in, some kind of solvent, right? Methanol maybe. Right? If we put these two together here, right, then there was an interesting result. And you say, okay, well, what's going on here, right? So the product that got formed looked like this. You say, well, why would this be the observed product, right? Why would we expect to see something like this here? Well, let's think for just a second, right? Let's think here for just a second. So what we did is we added, right, in this case, in this example, right, we added at the beta carbon there, right? There's our alpha carbon in red, our beta carbon there in purple. So what happened in this case? Let's see if we can back out a mechanism here. So if we bring in methoxide, okay, let's send that in here. We know it has to get added there, right, because we see our product. Let's see what would happen then. Well, we make a bond, we break a bond. Let me do this in yellow here. So let's send that up, right? Let's send up the pi bond into a lone pair there on our alpha carbon, right? So let's see what's going on here in this step here. So there's what we have. We made this, right? There's that. Purple here, red here, and we ended up making a lone pair and negative charge, right, on that alpha carbon. And remember, anytime you make a charge, right, the question is always, can we stabilize it? Can we spread it out? Can we do something? Can we do something with this? And hopefully at this point, if you've been paying attention for the rest of the lectures, right, we can see that very easily, right, we can do this. So let's draw this out. So we made an enolate, right? Which would quickly tautomerize, right? Which would quickly tautomerize into our product up here, right? So let's do our mechanism here then properly, right? So we send in something at that beta carbon, we shift, right? And that takes us to here. So what we find is that we have something called 1,4 additions. Now, we've talked about 1,4 additions before when we talked about thermodynamic and kinetic products. So this isn't an unusual concept. Remember, when we were talking about thermodynamic and kinetic products, we took a look at stability of the product, right? As we add some heat, we can go through an extra resonance structure, right, and make a stable intermediate, in that way. So go take a look at thermodynamics versus kinetics. I can't, do a recap of it right now, but we've seen these 1,4 additions before, is what the point is. So let's do a quick observation here, real quick, right? Let's kind of drive this point home one more time. If I have my generic enone, right? If I just have it on its own, right? I can push electrons around to generate this guy right here, right? Whoops. To generate this structure here, where I have a positive charge on my beta carbon there, right? So here's my beta carbon, right? Alpha carbon, alpha carbon, alpha carbon, right? So it looks, I've got a positive charge there on my beta carbon, so it makes sense that something negative is going to add there, okay? This doesn't mean that we shut down any reaction that happens at the carbonyl carbon, right? I'm just saying we can do, under certain conditions, right, we observe addition at the 4 or the beta carbon of these alpha beta unsaturated ketones, or the enones, okay? So depending on the reagents that we add into this, we can start to add, right, we can start to add to the beta carbon. There's a couple of terms for this. We can call it a conjugate addition, or the book talks about Michael additions. So Michael additions or conjugate additions. These are kind of terms for all the same thing here. Although Michael addition technically is a specific set of reactions, a Michael addition is a specific conjugate addition, or a specific 1,4 addition, where we bring in a carbon with a negative charge, right? So we have a carbanion which comes in and adds at the 4 position there. And so, and that should be the important key part to kind of remember with this, right? So if we recall, one of the important reactions that we want to talk about is how we can make carbon-carbon bonds, and a Michael addition is a very good example of this, right? So okay, so how can we start to get this done, right? Let's talk a little bit more about Michael additions here and what is going on. So there's 2 parts to a Michael addition, which we kind of need to talk about. There's Michael donors and Michael acceptors. Now, you might be asking, why are we only looking at Michael additions or anything? To be honest, there's a lot of reactions that go through these conjugate addition mechanisms. It really depends on the reagents and the conditions and all this kind of stuff, right? And so there's a lot of, we could sit here and talk a lot about conjugate additions, and if you do a quick Google search, right, you can find a bunch of information about it. But, Michael addition tends to be one of those that's, let's say, the most tested, I guess, if that makes sense to you guys, right? What do we expect to see the most often on some of these kind of standardized tests, and Michael additions tends to be there. So it could be that that's why we tend to focus on these a little bit more, right? They're just kind of the quintessential reactions for these conjugate additions, right? So that's often why some people just say Michael additions are any 1,4 addition, but that's not specifically true. Okay, so let's talk about Michael acceptors. Now, a Michael acceptor is kind of the easier end of things. This is really almost any enone falls into a Michael acceptor classification, right? So we were chatting about Michael acceptors, right? We have the enones here, right, which is the ones that we've been working on. These tend to be better with electron withdrawing groups. So things like esters, or maybe even aldehydes or any, if you put some nitro groups or fluoro groups, right? Things that are withdrawing electrons away, right? So if you put an electron withdrawing group there, things that are drawing electron density away from these pi bonds are going to make these acceptors more susceptible to attack. And so in that sense, you can even see some reactions where you have, this right here could do a Michael addition. You have that cyano group, which is withdrawing electrons away from that alkene there. And so I mentioned this to ask you guys to go back to look at the discussion that we had about Diels-Alder reactions. Because in our Diels-Alder reaction, we talked about electron withdrawing groups and the effect on the dienophile, right? So the dienophile. So that's where we originally talked about electron withdrawing groups and all that and how they affect the pi bonds and the resonance structures and all this kind of stuff along the way. So go back and see if you can remember about electron withdrawing groups and kind of apply those same principles here to these Michael acceptors. The most common ones are probably going to be these enones here. And we learned how to make those in this chapter, right? But we can also see things like with cyano groups there. Now, Michael donors are just tend to be carbons with negative charges. But again, we have to stabilize that negative charge, right, to make it a little bit softer, if you want to think about it like that, right? So a lot of the Michael donors, let's just walk through a couple of them here real quick. So Gilman reagents. So Gilman reagents are good examples of Michael donors. Gilman reagent, right, is our copper lithio complexes there. Remember, we saw those in the coupling reactions. But these are going to be, let's call them, air quote, softer alkanes, softer carbons with negative charges. So that these are going to add to the beta carbon of a Michael acceptor there. So if we go back to something like this, right? You say, well, wait a minute, I don't see any carbon with a negative charge. Well, if we deprotonate that central carbon there between that dione, right? If we deprotonate this with some kind of base, right, we end up making a resonance stabilized carbanion, right? Those blue hydrogens out there are very acidic. They tend to have a pKa, in the 10 to 12 range, right? Those are pretty darn acidic. So if we make some of these softer negative charges, those tend to be good donors, right? So that's what we're looking for: carbons with negative charges and donors, and then the acceptors are these unsaturated, enones, or any pi bond that's got an electron withdrawing group can do a Michael addition also under specific conditions. Okay, so let's go through an example real quick and take a look at one of these examples that we can have here, and then see what's going on, right? So let's say that we have this guy here, and we're going to react that with, let's do this in green. All right, that guy there, right? Good stuff. So now to get this to work, right, we're going to need to add a base into this. And so, you could pick any variety of bases here. Let's just use, just to keep things simple, let's say that we're going to add some hydroxide to this, right? Okay, so where do we begin with this? Well, if we have some hydroxide, we've got these ketones around, right? We're looking for we're looking for some acidic hydrogens here. And so let's take this hydrogen right here, right? Let's take that guy right there. And let's pop that down. And I'm going to skip drawing it because I'll assume you guys can do it at this point, right? But we can stabilize the enolate with this, right? So now, right, we've generated a carbon with a negative charge, and we can delocalize that through an enolate, right? So we're looking at a similar situation as to this here, right? Not as good as that one up there in terms of soft negative charge, but we've got a carbon that's a delocalized negative charge, right? So now what we're going to do, once we've generated our negative charge, we're going to add it to our beta carbon, right? There's our beta carbon right there. So let's do a flow of let's do a flow of reactions here. Okay. So let's draw what happened. There's that. Here's this, right? That's my new bond that got formed there. I hit my beta carbon. That's that one there. My beta carbon's attached to my alpha carbon. There's my O, and there's my phenyl right there. Okay. Let's fill in. Here's our pi bond, and there's our negative charge right there, right? And then if we have some kind of proton source in here, an alcohol or some water or something like that, right? Then we can go through and we can basically give this some kind of proton source here, right? We can give this some kind of proton source to where we have that, right, which will tautomerize into our final product, right? I'm going to draw this slightly differently here just to make it look a little bit. Cool. Okay. So there's one example. Now we have to be careful, right? Because, where our alpha hydrogen is deprotonated, right? Why did we pick that yellow one there? All these kind of things. We have to be careful when we're doing these Michael additions to make sure that, one, we don't lose any carbons. Two, make sure that we're grabbing, or we're attacking the carbons at the right place and not losing anything along the way, right? So these can get pretty complex, but these are extremely useful reactions to adding alkyl groups at beta positions, right? At the 4 positions of an enone or an alpha beta unsaturated ketone there. Now, truth be told, there's a million different conditions for Michael additions. And if you do a quick search, on Google, right, you'll see that there are a million different conditions for this. And so it might not be a bad idea to kind of go through and take a look at some of these, right? But this is just kind of a standard example of it. Like, what are we doing, right? Okay. And that's honestly about it for chapter 22. There are a couple of other reactions that we didn't explicitly talk about that are listed in the chapter. It'd be good to look over those just so you kind of recognize them, but we're going to kind of not include those in the discussion that we have for this semester. So that is all I wanted to give you guys for lecture for chapter 22, and that'll be it for today then.